Okay. Before we start with a revision on heat transfer processes, do you have any question concerning the introduction, chapter 1? So in chapter 1, you have introduction of the main forms of energy and the history of energy. And we will see how energy can be transformed from one form to the other in this course. This is why it's very important to understand the different processes through which we can have heat transfer. Because as you know, we need to write like an energy balance. So we need to understand the different forms of energy. And this chapter will be a revision of the different heat transfer processes, how we calculate them, how we make an energy balance for a system, etc. So to start with, we know that heat transfer will seek to predict the energy transfer that can take place between material bodies as a result of a temperature difference. And we have a lot of application in this course that are related to heat transfer. If we take simply the example of solar energy, let's say we have PV cells. These cells will receive radiation from the sun, and then a part of this energy will be absorbed, and we have like a water or refrigerant that will circulate through under the solar panels to take this energy. So it's a form of a heat exchanger if you want. So we need to understand how heat is transferred first, how it's absorbed by radiation effect, then how it transferred to water by convective heat transfer, etc. So to understand how energy will be transported from one state to the other, it's important to know the basics of heat transfer. And if we consider another application, let's say buildings, when we construct buildings and we want to decide on the material types. So in the envelope, we put several layers. How we select these layers, their thickness, the type of material. For example, we'll see together that if we put two layers of brick and between them, we consider an air layer, this will enhance a lot the insulation properties of the envelope, because air is a bad conductor. It's characterized by a low thermal conductivity, and in this way we will reduce heat losses between the inner and outer space. So a lot of applications related to energy in buildings will involve heat transfer processes. Thermodynamics teaches that energy transfer is defined as heat. In this course, we'll see, if you want, the transient behavior of temperature variation, how we go from one equilibrium state to another by understanding the different heat processes, the storage of energy, the delivery of energy, and the transport of energy. Please stop me if you have any question. So to start with, the main three modes of heat transfer are conduction, convection, and radiation. And these processes can be involved at the same time, but in different media. What I mean by this, in general, for example, let's say if we go back to the example of the envelope, okay? We have the envelope and it's exposed from the outer side to T out, and from the inner side to Tn. Let's say you know that mainly the heat received from the sun is by radiation effect. So the sun will emit electrowaves that will reach the surface of the envelope by solar irradiation. We'll call it, the symbol of solar irradiation is G, as we'll see in this chapter. Now, a part of this irradiation will be absorbed by the material. So what we'll get in is alpha times G. And at the same time, we have also air surrounding the envelope from the external side. And if we have, let's say, wind motion, or even if we have still air with negligible velocities, we have what we call the free convection. So we have convection of heat by air, and at the same time we have irradiation coming from the sun. These heat fluxes can lead to energy that will come from the outer to the inner environment in summer, and it will be conducted through the envelope. So it will, if you want, it will be transported within the solid material of the envelope by conduction. Now, in case we put an air layer, and we'll discuss this together after, we can have also convection inside air, okay? But inside the fluid, inside the solid, we don't have conduction. And if you have here a solid material, the heat will be transferred only by conduction. Now, within the air layer, you can have both conduction and convection. This is why we'll discuss after what is the optimal thickness of air layer. If you increase a lot the thickness of the air layers, this will give a negative effect, because your purpose from the air layer is to create insulation. Okay, but because the air is characterized by low value of K. But if you increase a lot this thickness, you will give a freedom for molecules of air to move, and this will create convective currents that enhance instead of reducing heat transfer within the envelope, they can increase it. This is why we'll see how we can appropriately design the air thickness to enhance the insulation of the building envelope. So in this simple problem, we can have conduction, convection, and radiation. At the free surface, heat is absorbed in form of convection and radiation, and it will be transported to the inner space by, if I have only a solid material, only by conduction. And if I have a fluid, by combination, let's say, of conduction and convection. In this small example here, another example, we have also different processes that are involved. If I want to heat water, okay, I just have to put it under fire, and then what will happen is that all modes of heat transfer will be involved. The main one here in this example is radiation. Why the main one is radiation? Because you don't have contact. You have a distance between, if you want, the fire surface and the bottom of your container. So mainly heat is transferred from fire to the surface, to the bottom surface, by radiation effect. As you can see, these are the electromagnetic waves emitted from the fire reaching the bottom of the surface of the container. Second, why we have convection here? Can you explain for me why we have convection in this example? Do you remember convection is connected with what?
Because water is moving.
Very good. Convection is always related to fluid motion. And we have several types of convection. It can be natural, it can be forced, as we will explain in a while. Mainly, in this example, we have a fluid motion because of a density variation. What will happen when we heat, the molecules at the lower level will have larger temperature and relative lower density. So at the bottom level, you will have lower rho, and colder water at the upper side will have a higher density. And you know that if you have high density above, molecules of water will tend to move downward to replace the hot molecules. And this will create like circulation of the fluid, because water molecules that are at the top level are relatively cooler. They will tend to replace hot molecules, so they move down. As they move down, they will be heated by the surface, and then they will become with lower density, they will move up again, and this will create like a random circulation of fluid within water, and this will lead to heating by convection, because like you have a mixing effect. And also here we have heating by conduction. The conduction, we can see it at this level because your hand is in contact with the metal here. And also you have conduction in water, because whenever you create a gradient in temperature, heat will be transferred by conduction. But in general, in fluids, convection is more dominant, okay? But conduction is always related to temperature gradient of bodies in contact. So between the molecules of the fluids that have different temperatures, you will have heat flux also by conduction. But within water, convection will be dominant, as we will discuss after. So in this example also, all these processes are involved. Now we'll go into each process separately, and we'll remember what are the main formulas driving conduction, convection, and radiation. Because at the end, what is our purpose as application in this course? In any application having, let's say, energy transfer, heat transfer can occur in one of these modes, and then we will be able to write the energy balance for a system to understand how energy will be transported within our system. So first, if we start by conduction, conduction is mainly due to temperature difference, okay? Plus it requires contact. So I cannot have conduction without contact between objects, or at the micro scale, contact between molecules. So you will have, as we will see now, we'll have vibration of molecules characterized by larger temperature. And because of vibration, you have collision between molecules, which will lead to transfer of energy from the hotter side to the cooler side. So we can say that first, transfer of conduction requires direct contact. Conduction can occur anytime objects at different temperatures are touching each other. And this process of heat transfer by conduction will continue until reaching equilibrium, thermodynamic equilibrium. Thermodynamic equilibrium will be reached when the temperature of the different objects in contact will become the same. A very simple example of this, if we place a spoon in a hot cup of coffee, equilibrium is reached when the temperature of the spoon will be equal to the temperature of the coffee. Now, at the micro scale, to understand the conduction process, we consider the following example. You have a rod and you are heating side A. And then what will happen when you heat, energy, the heating energy will be transferred to the molecules, and it will be transformed into vibrational effect. So the molecules will vibrate, and then the frequency of collision between the molecules will increase. This is why we'll have transfer of energy due to vibration effect from the hotter side to the cooler side. So larger the heat transferred, larger will be the vibration of these molecules. Now, also conduction, of course, will be affected by the material. And if you heat, let's say, aluminum, it's not like you heat wood. Metals are very good conductors. They tend to transfer energy in a much more efficient way than other materials. And if we compare solids, liquids, and gases, conduction will be the most efficient in solids, because solids are characterized by relatively shorter distances separating molecules. And you know that conduction is directly related with contact between two objects, so contact between molecules and atoms. This is why for a solid, since the mean free path and distance between the molecules is relatively small, vibration will lead to a higher frequency of collisions, and this will lead to a very simple transfer of heat. While in case of liquids, this distance become larger, and for gases, it is larger and larger. This is why, in general, gases are characterized by much lower conductivity than liquids, and liquids have smaller conductivity than solids. Now, if we want to put it in a equation form, we should know what are the main parameters affecting conduction. So we go back to the simplest scenario, which is heat transfer through a solid. If I have a wall and I impose different temperatures in the inner and outer side, of course, always heat will flow from the largest temperature to the smallest temperature. Okay. Now, in case I don't know if T1 is larger than T2 or T2 larger than T1, I can write a general equation that can work in all cases. This is why I select a positive direction. Let's say I consider this is the positive x-axis. And I want to come up with a general formula for heat flux that will work if T1 is larger than T2 or if T1 is smaller than T2. So I can write the following. I can write that Q second. This symbol second means per unit area. So the unit here will be watt per meter square. Q second is equal to minus K times A times the gradient of temperature with respect to x. So times dt by dx. Can you tell me why we have the minus here? Why we are putting minus and not just Ka dt by dx?
Temperature and
temperature is decreasing.
Yes, the flux is always in the direction opposing the gradient of temperature. This means that if T1 larger than T2, what will happen? dt by dx will be negative. Okay, but the flux will go from side 1 to side 2, so it will move in the positive direction. So when dt by dx is negative, the flux will move in positive x. And when dt by dx is positive, the flux will move in the opposite direction, in the negative one. This is why we have minus dt by dx. Okay, now I did a small mistake. Who can tell me what is wrong in this equation here?
There's no area.
Yes, if I want to put A here, I should put Q second times A, and instead of having the heat flux, I have the heat rate, Q. Okay, so if they ask you to calculate the conduction heat rate, then you just find the value in watt. It's minus Ka dt by dx. If they ask you for the heat flux Q second, you just do minus K dt by dx. Now, as we said, the conduction also depends on the property of the material. So K will tell us if it's a good conductor or if it's a bad conductor. So conduction flux is affected by the conductivity of the material and the gradient of temperature. And if I talk about the conduction rate, larger the area, larger will be the rate of conduction. And this area is perpendicular to the heat transfer by conduction. And for example, in the case of wall, the area is the cross-sectional area of the wall that is perpendicular to the heat flux. Okay? So this is the area that we consider. Any question on this? Okay. Now, let us start by considering simple cases in which we have unidirectional heat transfer. In general, heat transfer can take place in 3 directions, so it's a 3D process. But in a lot of applications, temperature gradient is mainly in one direction. So we can then take the assumption that heat transfer is negligible in other directions. Let us consider the following problem. So when we impose different temperature from the inner and outer side, we can say that if we move in the perpendicular direction to the thickness, no change in temperature, because there is no source of temperature variation in this direction. And even if we have it, it's really negligible. So if you consider the room inside your space, if you take measurements at different locations, you might have variation in temperature, but this difference is really small compared to the gradient imposed between the inner and outer side. So you can say that change in this in y and z direction is negligible compared to change in x direction. This is why I will model this problem as a unidirectional heat flow. And then from Fourier's law, Q second in x can be written as minus K dt by dx. Now, if I tell you you have a steady state problem, what do we mean when I say it's a steady state problem?
The flux isn't changing.
No change in temperature. Okay, please pay attention. Here, it's true what you said in this problem. In this problem that I gave you, the flux is not changing. But if I have another scenario, and I will explain in a while what I mean, you can have steady state, but the flux is changing. Okay, and we'll see how. So whenever we say steady state, this means no variation with time. Okay, but I can have variation with space. Okay, so here it says whenever I say steady state problem, the first conclusion that you can make is that you have no variation with time. But to state that the flux is constant, you have other conditions. Okay, so steady state, no variation with time. Now, how to know if the flux is constant or not? I should look at my problem to see, for example, if there is energy generation within my system. If I have, let's say, for example, how we can have generation. Let's say I have insulation from this side. Okay. If I insulate the wall here, and I have a reaction, a chemical reaction, or I have, let's say, if we take another example different than the wall, you can have, for example, combustion in this place, for example, and you have heat release. Or if you have an electrical application, you can have a wire, an electrical wire where you have a current passing through it, which will generate heat. So you can have, for certain application, you can impose generation of heat. Okay. Let's say the generation is in a volume. And I tell you, for example, in this problem, I have a heat generation Q, volumetric. This means this generation QG is in watt per meter cube, volumetric generation. And I have steady state problem. So I can have steady state even if I have generation. When I say steady state, if I look at a certain position with time, there will be no change in the temperature at this position. But if I look at another position, of course, I will get another temperature, etc. And the flux of conduction then will not be constant through the wall. If I have generation, it will be variable. Can you tell me physically why it will be variable? How can I demonstrate this? Okay. The purpose of this chapter is to help you to answer such questions. I need to make an energy balance. Whenever I make an energy balance for my system, I will know what is entering this system and what is exiting this system. When I say I have a steady state case, this means there is no storage. As we discussed together in this course, we are interested in energy storage, energy transport, and energy distribution. Okay? So whenever we consider the storage effect, whenever we have storage, this is directly related to variation with time. Because if I store energy, I cannot be at steady state. The temperature, let's say, will increase if I take it in sensible form. What is sensible heat? What is the difference between sensible heat and latent heat?
Sensible is based on delta T, but latent is for change of phase.
Very good. We'll see together also in this course that one very important field is the one of storage, where you have phase change material, or where you have change of phase. Whenever you rely on change of phase to store energy, then you are dealing with energy transfer in latent form. And the idea of latent energy is very important, especially in building applications. Why? Because let's say if you have a material, for example, we have what we call PCM, phase change material. Okay. The phase change material is characterized by the following. For example, let's say it's encapsulated within the envelope. What will happen then? You have here, let's say, a liquid. Okay. And this liquid can be transformed at at normal temperature, and we select an appropriate material that can change phase in normal temperature conditions. So let's say it's in liquid form. To be transformed into solid, it should lose energy. Okay, so for example, during the night, you have low temperature in the room. Okay, T of the temperature of the room is relatively low. So what will lower than the envelope. So what will happen then? This liquid will be transformed into solid and will release heat to the room. While during the day, you have especially during summer, you have high temperatures from the energy radiation of the sun that is absorbed through the envelope. Heat can be stored in this material, but it is stored in which form? In latent form, because once absorbed, this heat will lead to change of phase from solid to liquid. And in this way, you avoid having large gradient in temperature in your room. Why? Because let's say if the outdoor temperature is really changing, so during the day you have high temperature, during the night you have much lower temperature. So if you observe the profile of the outdoor temperature, you have large fluctuations, which is bad for the comfort of people. Inside the room, we try to ensure acceptable variation in temperature. So if we don't put anything here, if we have a weak insulation, what will happen is that in the indoor environment, we will have also a large variation of temperature. Of course, not like the outdoor temperature, because you still have a certain resistance. But if the resistance is not very high, you can have high fluctuations within your room. This is not desired. Okay, to avoid this, we work on enhancing the structure of the envelope. So larger the resistance, you can reduce this fluctuation, and you can produce what we call, if you want, the thermal lag effect. Yani the increase will be slower and the decrease also will be slower. Now, to enhance this performance, when you store energy in latent form, you can maintain a relatively temperature that is much closer to the average, because latent heat will take place at constant temperature. And you know that if you have ice and you want to transform it into water, as long as you have ice, so when you have mixture of ice and water, you can maintain the temperature at 0 degrees in ambient conditions. Okay, of course here we'll not use water, because we don't want to have the change in phase at 0 degrees. We want to have it, for example, at 20 degrees. Okay, so we select a material that can do change of phase at 20 degrees. So what will happen then is that during the day, you have storage in latent form, because your PCM will absorb the heat and will go from the solid state to the liquid state. Of course, we have what we call saturation. When you reach 100% liquid, okay, you will start to have increase in temperature. But at least until reaching the state, you were able to maintain a stable temperature. This is why we have what we call the lag effect. So the increase in temperature in the space will be much lower, okay? And it will be slow. So you will have more time to increase the temperature and more time to reduce the temperature. And then you dampen the oscillation profile that you had before putting your PCM. So all of these, to understand them, we should know the basics of heat transfer, because we'll use this a lot in our applications. So going back to our problem, we were talking about generation. Whenever we have generation of heat, let's say I told you have a certain generation within your wall, Q generation, okay? If you want to understand what will happen, you need to take a control volume and state what are, if you want, the fluxes coming in and what are the fluxes getting out. Example, let me consider at any location X, my control volume. If I do a cut here, I am interested in this zone. So between the insulation, so we said we have an insulation here. And we have generation, a volumetric generation given in watt per meter cube. Okay, and I told you that you have steady state. Whenever you have steady state, you can say, as we said, no storage of energy. If you don't have storage of energy, what can you say then? What is, if you want, the equation that you can write if you don't have storage?
N equals out.
Very good. So you can say that summation of energy fluxes in, or rate, energy rate in, is equal to summation of energy rates out. And if I want to take my example, I already know that I have insulation from this side. So do I have any possibility of energy coming in from this side? Do I have an inlet of energy here if I have good insulation?
No, no.
No.
No, we don't.
Okay, we don't have. So for this surface, we are fine. Now, at this level, what will happen? Heat will be transferred out. By which type of heat transfer it will go out of this surface? By conduction?
Conduction.
By conduction, because I am within the solid material. So this is a Q conduction at location X, and we will see together that if we have generation, this Q conduction will vary with X. So I will call it Q conduction at location X. Now, what I can say also here, if you want, instead of just putting some En, I should add something here, which is similar to the inlet if you want, but instead of coming from outside, it's generated within the system. So I can put that sum of energy in plus sum of energy generated. I have a source of energy within my system, okay, that is leading to the presence of energy inside my system. So some of what is coming in plus what is generated within the system should go out to have no storage. Okay, so here in this case, because I told you have a volumetric generation, you should say I don't have inlet in this problem. I don't have possibility of energy coming in from outside because I have because I have installation here. But because of generation, I have this term. And this generation is simply calculated as the volumetric flux that I gave you, Q generated per unit volume, times the volume of my system at position X. So times Vx. This is equal to Q conduction at position X. So this is the energy balance. The energy balance told me that the conduction flux here is affected by the location. Why? Because this volume will change with location. If I want to express it at any location X, I have the thickness here equal to X. And of course, I have the area, let's say, of my wall. So the volume will be A times X. So I can deduce that Q generation per unit volume times AX is equal to Q conduction at location X. So from here, we can see that it's true that it's a steady state application, but the conduction flux is not constant, it's varying. And at X equals 0, I am at the insulation. So as I can expect, at the insulation level for X equals 0, I have, if I replace in my formula, Q conduction is 0. And this is expected because I have insulation. And larger is X, larger will be the conduction flux. This means that the largest conduction when I have generation in this example will be at the outer surface. Okay, at this surface. And this is also physically, it's a very logic phenomena. Why? Because if I consider that heat should be dissipated, it cannot be stored. Okay, I don't have possibility of storage, and I have generation within my system. Since I only have one way to escape, I am not able to have heat dissipation from this side. It's not possible because of insulation. So my only if you want, possible heat dissipation to the outer environment is through this surface. This is why the conduction flux will be maximum at this level, because here I will have dissipation of the whole energy that is generated in this volume. Okay, so this example was to tell you that depending on the situation, I can study how the conduction is varying. Now, if I don't have generation, all I have to do is to say then, if I go to my previous example, I have no generation. This means that I can write some En equal to some E out. So I don't have any generation then. And if I take any control volume now, but of course, I don't have insulation now. You know why? Because if I have insulation also, if I have insulation, this means that the temperature will not vary. Because insulation and no generation means that temperature will remain constant. But now it's not the case. I am imposing a certain temperature T1 here, and I have another temperature T2. I created a gradient of temperature. So, but I don't have storage, I don't have generation. So if I take any control volume now, and I put some the energy flux in, I have a conduction flux that is coming in, and a conduction flux that is getting out. And because I can write En equals E out, and I have only transfer by conduction, I can deduce that minus Ka dt by dx in at the inner side, or at x1 if you want. If I take a control volume between x1 and x2, so minus Ka dt by dx at x1 is equal to minus Ka dt by dx at x2. And because in this application, conductivity is constant, okay? And the area is the same because the cross-sectional area of the wall is not changing. So I can deduce then that here the conduction flux and rates are constant, okay? So whenever you have an application where you have no generation and no storage, steady state, and only heat flux by conduction, you have the right to say directly that the conduction flux is constant. هلا flux while لأنه area is the same. Please pay attention. Okay, always write the formula and then do simplifications. In this application, area is the same. If area is not the same, dt by dx will not be the same. And if you take, for example, a certain nozzle, okay, of this shape, area is changing. So in steady state